So we are very happy to have Maurice Brooks today, who will speak about the Fröhlich polaron at large coupling. Please go ahead.
Thank you very much. I very much enjoyed this opportunity to share some recent results on the Fröhlich polaron with you. So, of course, I want to present some mathematical results, but let me set the stage first. So let me talk a little bit about the physical picture. So the idea you have is you see the following picture. You have a negatively charged electron, and this electron travels through a polarizable medium. So what I mean with this is that the medium has a total net charge of zero. However, due to the electric field of the electron, it will attract the positive parts in the medium and repel the negative parts. So the picture we should have in mind is that while traveling through the medium, the electron is followed by a cloud of polarization. And this composite object, the electron, together with the attached cloud of polarization, this is what we call a polaron. Now you see the electron is allowed to move in unconfined space. So this means we describe its position by a vector in R3. Now, when we want to talk about the polarization field, the question of how to describe it is a little bit more subtle. And in the Fröhlich model, this problem is solved by describing the polarization in terms of a polarization field. So what we do is, at every point, say y in space, we measure the amount of displacement of the positive or negative charges, right? So the electron induces a displacement of positive charges towards the electron and negative charges away from the electron. And this real valued function phi should tell us at every point in space the amount by which the charge is displaced. Now you see there are many approximations going on in the Fröhlich polaron. Two of them we can immediately see. So the first approximation is that we take the medium as a continuous object. So in the picture you see something discrete, but then we say, okay, we want somehow the mesh size to go to zero, such that we can talk about a continuous object. And the second approximation we made, or one of the other approximations we made, is that you see the polarization field is real valued. So I only measure the amount of displacement. But really, if we think about a dipole, it doesn't only have a strength, it also has a direction. But I say, let's forget about the direction. This is just to do some simplifications. Okay. Now, another thing that is worth mentioning is that in the Fröhlich model, both the electron as well as the polarization field are treated as quantum objects. So this means, besides the Fröhlich polaron having a clear physical interpretation, it is also a popular toy model for a quantum field theory. Now you see, there are a few things I like about the Fröhlich polaron. So one of them is that it is a model that is simple enough to allow for rigorous mathematical results concerning things like, say, operator domain, spectrum of operators, unitary time evolution. All of these things you can derive rigorous results. However, while being simple enough to allow for these results, it is still rich enough to give rise to complex phenomena. And so there are multiple interesting things you can study for the Fröhlich polaron. The specific one I am interested in is that due to the interactions of the electron with the polarizable medium, its mass is effectively increased. So the picture you should have in mind is the electron is traveling through the medium. However, there is a cloud of polarization attached to the electron, which, loosely speaking, slows it down, which we interpret as the electron having an effectively increased mass. And to be more precise, I'm interested in how the effective mass depends on the interaction strength between electron and the medium. So in the following, I will always denote by alpha greater 0. This should always be a parameter which tells you the coupling strength between electron and medium. And in the end, I will be interested in letting alpha go to infinity. And then there is a quite well-known conjecture in the literature, which in the form I'm stating it here dates back to Herbert Spohn from around 87, which tells you that the effective mass as a function of the coupling strength alpha increases with alpha in the fourth power. So not only does it go to infinity, as alpha goes to infinity, it actually diverges with the fourth power. And this conjecture even includes a precise prefactor, which I call M subscript LP. And this precise prefactor in the strong coupling limit, this constant emerges from the underlying Landau-Pekar theory. Now you see, the Fröhlich model is part of a very exclusive class of models where, due to some scaling, the strong coupling limit actually coincides with the semi-classical limit. So instead of calling the underlying theory the Landau-Pekar theory, I could also call it the semi-classical theory. However, the Landau-Pekar, of course, explains the subscript LP in the MLP constant, and this is also the reason why I call this the Landau-Pekar Spohn conjecture. Now you see, so far I have defined nothing rigorously, right? So in the following, so now that the physical stage is set, I want to set the mathematical stage. And there are a few ingredients I need. So first of all, I need to define the Fröhlich model. As a quantum theory, a nice way to properly introduce a quantum theory is by giving you a Hilbert space, which encodes the states of our system, and giving you a self-adjoint operator Hamiltonian acting on this Hilbert space, which, as you know, encodes the thermal and dynamical informations of the system. Okay, so let me start with the underlying Hilbert space. You see, I'm talking about an electron which interacts with a field, namely the polarization field. So since there are two components, it is very natural to define my Hilbert space as the tensor. So the first factor in this tensor product you see, the L2 of R3, this is just encodes the possible states of the electron. While the second tensor factor encodes the degrees of freedom of the polarization field. And as we are well familiar from quantum field theory, the right Hilbert space to talk about a quantum field is a Fock space. And we take the Fock space over L2 of R3. Now, in the following, it will sometimes be convenient to identify this tensor product with the L2 space of Fock space valued functions. This is just convenient sometimes. Okay, so we have our Hilbert space. Now you see, this Hilbert space involves a Fock space. And whenever we talk about Fock spaces, we have to talk about at least one class of iconic operators defined on this Fock space. So this is just that, okay, maybe as a comment, I can write this Fock space. I can sort it by the n particle sectors, right? So the n phonon sector of this Fock space I can write as L2 functions with 3 times n inputs. Now, what I wanted to say is that an exceptionally important class on this Fock space is given by the annihilation operators, and their adjoints I will call by the usual name creation operators. Now, you have probably all seen the definition, but there is a tiny twist to my definition, so I will write it out explicitly. So for a given coupling strength alpha greater 0 and a given L2 function, I define the annihilation operator acting on an n particle function by simply freezing n-1 coordinates, taking the inner product with the given function f, then multiplying with square root n. This is all standard, and now comes the tiny twist. I divide by the coupling strength. So I find it convenient to bake the coupling strength into my definition of the annihilation operators. And the only reason to do it is so that the formulas look more clean. I mean, there is no deeper reason. Okay, so we have annihilation operators. They are great. There are, however, two more families I want to mention. So the first thing is I also want to define the polarization field operators, which is basically just you take the annihilation operator, you add the adjoint, and this I call phi of f. And this phi is the quantum counterpart to the polarization field I've shown you in the first picture, right? So okay, out of create annihilation operators, we can immediately form the polarization fields. And then I also want to introduce the second quantization of a one particle operator. And this is just you take a one particle operator A and you let it act on each individual constant variable and then you add them up, right? And actually, I will only need two specific instances of the second quantization. Namely, I want to introduce the particle number operator n, which is just the second quantization of the identity. Again, tiny twist. I bake the coupling strength into this definition. Okay. Again, it makes the formulas look nicer. And then the second kind of mm, second quantized operator I need is the field momentum operator. So capital P, this is for momentum. The subscript small f stands for field. So this should represent the momentum of the polarization field. And it is just the second quantization of the one particle momentum operator. Okay. And with these ingredients, I have everything at hand to properly define the Fröhlich Hamiltonian, which acts on the Hilbert space I've shown you earlier. And you do it in the following way. So first of all, our Hilbert space are Fock space valued L2 functions. And then I define the Fröhlich Hamiltonian as the direct integral over the p-dependent operators h, where this subscript p, the p stands for the total momentum of the system, and we integrate over R3. And each individual HP is defined with these three components, where the field operator takes a function v as an input, and you see the function v is simply defined as some constant times y to the power minus 2. And you might immediately recognize this function 1 over y to the power square as the strength of the electric dipole field. So this is the connection to the polarization field. Now, in case so you have seen I've used this, let's call it fancy notation with the direct integral. This is just some twisted way to say that these operators HP act pointwise. So what I mean with this is H applied to some Fock-based valued function psi, evaluated at P, is just you evaluate psi at P and you act with this fiber operator HP on this specific vector. Okay, this is the definition. Now, let's break down the three individual terms you see. So each fiber operator HP includes the first term, which is the total momentum small p minus the field momentum squared. Now, of course, if you take the total momentum, you subtract the field momentum, what is left is the momentum of the electron. So electron momentum squared is just the kinetic energy of the electron. Okay, great. So the first term you see here is just the kinetics of the electron. The second operator is the particle number operator. And in the Fröhlich model, this represents the internal energy of the polarization field. Okay, so first term is kinetic of the electron. Second term is just the internal energy of the polarization field. The only thing that is missing to have something non-trivial is an interaction between the two subsystems. And the interaction is given by this polarization field evaluated at the function v. Now, you should be a little bit skeptical about what I've just told you. Because you see, if you look at the polarization field, this only acts on the Fock space, but not on the R3. So you might ask, why is this an interaction with the electron? And this is due to the coordinate system I've chosen to define my Fröhlich Hamiltonian. So the thing is, I've defined the Fröhlich Hamiltonian in a coordinate system where I measure the polarization field relative to the electron. So what you do is you follow the electron, you stand on the electron, and from the position of the electron, you measure the polarization field. Now, if you would rewrite the Hamiltonian in a stationary frame, which is mathematically done using the Lie-Low-Pines transformation. So if you would apply the Lie-Low-Pines transformation, you would see that instead of this function v, you would have the function v where you evaluate at y minus the electron position x. So the point is, I'm defining the Fröhlich Hamiltonian out of convenience in a special non-stationary frame. But if you would do the transformation backwards, you would see that the final term, this field term, is actually an interaction between electron and polarization field. Okay. You see the advantage of working in this special coordinate frame is that you immediately see that this operator H commutes with the total momentum variable P. So in this way, it is clear that the operator commutes with total momentum, and yeah. Now, there is actually a second thing you should be skeptical about. The second sketchy thing I have done is I've said take the field momentum evaluated at V. But you might of course say that the function V is not in L2. But I've only defined annihilation operators for functions V that are in L2. So the problem with this function is that it has a mild ultraviolet singularity. However, the point is you can cure this singularity and it's actually very tame. And I do not want to say too much on it, but I do want to show you the main steps. So, so in this slide and only in this slide, I will quickly talk a little bit about how you can avoid ultraviolet problems. And what you do is, first of all, you observe that the annihilation operator is still well defined in case you take an n particle function psi that is a test function. So let's say compactly supported and C infinity, and f is a distribution on R3. Then this definition makes sense pointwise, and the function you get here is still compactly supported and at least continuous. Okay, so with this at hand, I can now define a quadratic form. This should of course be the quadratic form associated to the Fröhlich Hamiltonian in the end. And the first two terms are clear. I mean, it's just the total momentum minus the field momentum squared applied to psi. This makes perfect sense. Also, the particle number operator is perfectly well defined. The only twist is that this operator A of V, the adjoint actually has trivial domain. So it doesn't make sense to talk about the adjoint of this operator AV, but instead of talking about the adjoint, I just take 2 times the real part, which at least formally corresponds to AV plus AV adjoint. Okay, so this is the trick. You can still define the quadratic form. However, I do not only want the quadratic form, I really would love a self-adjoint operator. And there is a general recipe, the Friedrichs extension, which tells you if you have something semi-bounded and closable, then you are in a good shape. You can still define a corresponding self-adjoint operator. And this is a very nice argument that goes back to Lieb and Yamasaki, and this is at this point quite a while ago. And this argument essentially tells you that the interaction term is infinitesimally bounded with respect to the non-interacting part, and the non-interacting part is just the field momentum squared plus the particle number operator. Now, for the experts in the audience who know this paper, it is usually formulated in the stationary frame. The fact that here is not the Laplace of the electron, but the field momentum squared is just because of my choice of coordinate frame. But it's one-to-one the same argument. Okay, so since this is infinitesimally bounded, you are in a good shape. The operator is semi-bounded and closable, and this means we find a self-adjoint operator such that if you take psi, h psi, this inner product, okay, it's identical to the quadratic form applied to psi for every psi in the domain of the self-adjoint operator, HP. Okay. Now you see, in some sense you could say, okay, I only want to talk about ground states energies in the end, so maybe it's not so important that there is a self-adjoint operator and we could just study the quadratic form. But the point is, this argument, this will repeatedly appear in my analysis of the system. And in particular, these kind of arguments tell you where your ground state concentrates, right? So since there's an infinitesimally bound with respect to p of square and n, you know that the expectation value of the particle number operator and also of this p of squared, they are reasonably bounded for your ground state. So really this Lieb-Yamasaki argument gives you very precise information about where you can find your ground state in the Hilbert space. Okay. Now, at this point, we have a proper defined self-adjoint operator, and I can now finally start discussing the definition of the effective mass. So in the following, I want to talk about spectral quantities, and the most elementary spectral quantity would be the ground state energy, but I define it as a function of the total momentum P. And how do I define it? Well, I simply define it as the infimum of the spectrum of the P fiber operator. Now, I think I don't have not written it down, but if you see this E alpha without a P, I mean the total ground state energy. So this would be the infimum over E alpha of P over every P, right? And has actually been proven that this function E alpha of P takes its total minimum at P equal to 0. Okay. So having the momentum-dependent ground state energy at hand, I can now give you the definition of the effective mass. And what you do is, you see the following formula, where you let the momentum go to 0, and you define it as the quotient of p squared divided by 2 times the energy increment. Now, let me say a few words about this definition. So first of all, we have to ask ourselves whether this is a sensible definition. And one quick sanity check, which we should definitely do, is what happens if I plug in for the energy of a free non-interacting particle. And if you do this, you know the energy of a non-interacting particle is p squared divided by 2 times its mass. So if you would plug this in, you would just recover the mass of the particle, which is good. I mean, so for non-interacting systems, our definition of the effective mass is actually identical just to the original mass of the particle. So this is already a good sanity check. However, I think this whole definition can be explained much better in terms of a graphical picture. Namely, what you try to do is the following. So here I have, in quotation marks, plotted you the energy E alpha as a function of P. Now, as a disclaimer, this is not a numerical simulation or anything of the sort. These are just functions I have chosen by hand to make the picture look nice. But so what you do is you take this energy as a function of P and you try to approximate the blue curve by the energy of a non-interacting particle. So the red curve is P squared divided by 2 times the effective mass. And you try to choose the effective mass in such a way that you have an optimal and quadratic approximation of the blue curve around 0. So you just say you have the true energy momentum relation and you try to fit in a quadratic approximation. And this gives you the definition of the effective mass. Now,
Maurice, can I
yes,
ask a question?
yes, please.
So alpha is the coupling constant, but it's not easy to see from your Hamiltonian because it's sort of hidden in your inner product and also to this definition of n.
Yes, right.
N is the usual Phonon number divided by alpha squared or something like that.
Yes, right. So maybe as an orientation, E alpha of P in the limit alpha to infinity will converge to a constant. So something not, yeah. So the natural scale is order 1 energies. And then this variation you see here is on the order 1 over alpha square. So yeah, exactly. So the green line, this is what I wanted to say just, is the bottom of the central spectrum, which starts at 1 divided by alpha squared, because this is the spectral gap of the particle number in my definition.
Okay. Right. Thank you.
Yes, so exactly. Energies are usually order 1. And what we see here, yeah, the green line is the bottom of the central spectrum. And okay, the ground state energy, of course, lies under the essential spectrum. And it's actually conjectured that for the Fröhlich Hamiltonian in 3 dimensions, that the blue line actually merges with the green line at a critical value of momentum. Now, as far as I understood, this has only been proven for small couplings alpha. So for alpha below some threshold alpha 0, this has actually been proven. I think in general, this is an open problem as far as I'm aware of. But maybe I can also tell you about a consequence of my work together with Robert Zeiringer. Namely, what we showed was that in the limit of alpha going to infinity, the blue curve follows the red curve until the intersection, and then it follows the green curve. So if you really take the limit alpha to infinity first of these objects, then the graph you would see would be the minimum of the red curve and the green curve. Unfortunately, this tells you nothing about finite alpha. Okay, but at least we know in the limit alpha going to infinity, this picture that the blue line should merge with the green line is a quite sensible one. Maybe also in context to this, so one could make the critique that the definition of the effective mass I've given you here above is not really physical because this is like a quotient of some spectral quantities, and that it might be much more natural to define the effective mass as the reaction of the system to an external force. So you might define the effective mass by studying the response of the ground state energy to an external potential. And as far as I'm aware of, the equivalence between the spectral definition and this response to an external force definition have been shown for multiple models. And for the Fröhlich model specifically, it's a work due to Elliott Lieb and Robert Zeiringer, who showed that, okay, actually the spectral definition coincides with the definition using an external force, which could be considered more physically. And since I am already on the topic of alternative definitions of the effective mass, there actually is a truly different definition of the effective mass. Namely, you could also define the effective mass using the critical momentum where the blue line merges with the green line. So you could also take this critical momentum as the definition of the effective mass. And for finite alpha, it's actually known that this would give you a different effective mass. But it would now be an interesting question to ask if the two of them coincide with each other in the limit alpha going to infinity. So it would actually be an interesting question to see whether this definition of the effective mass using this critical momentum where the two lines intersect, whether this also satisfies a Landau-Pekar Spohn conjecture. And I think this is completely unclear as far as I am aware of. Okay, now there is yet another thing I want to mention why I like this Fröhlich model. And so the third reason why I think this is a very nice thing to study is that this problem has actually attracted different communities in mathematics. So I myself would say I subscribe or I'm affiliated with the functional analytic approach. What does this mean? Well, it means I like variational characterizations and I like operator inequalities and stuff like this. However, there is also a very, in the end, quite different approach to the Fröhlich Hamiltonian using a Feynman-Katz formula. So you can use a path integral formula to translate this problem, problem given in terms of operators into a problem talking about probabilities and Wiener measures and stuff like this. And it is nice to see that two communities try to work on somehow similar problems, but using very different methods. And I think you can see that a lot of things are much easier using functional integration, so tools from probability theories, and I think other things might be easier in the functional analytic picture. And I think the optimal thing is really to try to communicate with each other and try to understand the problem from the big view picture. So since I have already started to talk about literature, I want to give you very much hand-selected lists of results. And let me maybe make a disclaimer that the results I'm looking at are concern ground state energy and effective mass in the limit of coupling strength going to infinity. And I mostly concentrate on the effective mass. Okay. So the first result which I have to mention in this list is the result by Donsker and Varadan from 83, who were able to show that in the limit of alpha going to infinity, this ground state energy, so E alpha is the total ground state energy, converges to a constant, which I called E Pekar. And with this, I want to emphasize that this constant, just like in the Landau-Pekar Spohn conjecture, also this E Pekar emerges from the underlying Landau-Pekar theory. Or in other words, it comes from the underlying semi-classical theory. So Donsker-Varadan, they used the Feynman-Katz formula and were using methods in functional integration. To be precise, I think this the study of this of the Fröhlich Hamiltonian asymptotics, this has been one of the first applications of the theory of large deviations as far as I am aware of. So this is a very nice result. More than a decade later, Lieb and Thomas in 97, they basically reproved the result. The improvement they made is that they proved it with a explicit rate of convergence, which was in their case alpha to the power minus 1 over 5. So maybe let me comment on this. First of all, this is certainly not a physically reasonable exponent. The true second order is alpha to the power minus 2. And so for me, I don't think that having an explicit rate is truly the value of this paper, but I think it's very nice because it gave an alternative approach using functional analytic methods. And in my eyes, they are, once you know how to do it, the methods they used are very elementary, I would say. So in principle, there is kind of a two-step thing. So first of all, they used again the Lieb-Yamasaki inequality to reduce this infinite dimensional problem to a finite dimensional problem. And once you have a finite dimensional problem, you can just use standard semi-classical strategies to get the leading order asymptotics. And in principle, all of the things I'm going to show you will rely very much on these ideas that have been initialized in this paper from Lieb and Thomas. Now, coming back to an effective mass and making a jump again by 2 decades, we have the result from Lieb and Seiringer, who were able to show that the effective mass actually diverges as alpha goes to infinity. So to this point, right, we people were already believing that it should diverge with the 4th power, but it was not even known that it even diverges at all. So Lieb and Seiringer, they were able to show it goes to infinity. In their main result section, they don't write the rate, but I think if you would trace the paper through, you would probably find some rate. But okay, I think they don't even bother with writing it. And now, not much later, this result was improved by Betz and Polzer. So Lieb-Seiringer was again functional analytic methods. Now we go to Betz-Polzer, and then there we go back to functional integration. And they were improving this result, showing that it actually diverges with alpha to the power 2 over 5. Now, similar to this result from Lieb and Thomas, there should be nothing physical or meaningful about 2 over 5. I think this is just the exponent they found in their methods. And again, I don't think that that having this alpha 2 over 5 is the main improvement of this paper, but I think it is again very nice because it opened a new approach to the effective mass, or it follows a new approach using Feynman-Katz formulas and functional integration. And not much later, a work by Selke using again functional integration, where they were able to significantly improve this result, and they get almost the optimal alpha 4 divergence. The only twist is they had to divide it by log alpha to the power 6. Okay, so this is almost the optimal divergence, and oops, sorry. And again, not much later, in a work by Basaes, Mukherjee, Selke, and Baradan, they were actually able to show that the effective mass is bounded from below by something that scales with the 4th power in alpha and a constant c. So they were able to get as a lower bound the optimal divergence, namely the divergence in alpha to the power 4. So from a lower bound, the only thing that they could not see is that they could not prove that you can choose this constant c as the constant predicted in the Landau-Pekar Spohn conjecture. Now you see the last 4 results I've shown you, they were all concerned with lower bounds. Now in a work together with Robert Seiringer, we were able to show that the effective mass as a function of alpha is actually bounded from above by something that decays by something of the form alpha to the power 4 times the precise constant predicted in the Landau-Pekar conjecture plus something that is small to alpha to the power 4. So at this point, if you believe the Landau-Pekar Spohn conjecture, we have showed the optimal upper bound here, and the lower bound is almost perfect. The only thing that was missing at this point is the precise constant in the lower bound. And so this was the contribution of my most recent work on the Fröhlich polaron, where I was able to show that, okay, the effective mass is bounded from below by something that diverges with alpha to the power 4 with exactly the constant predicted in the Landau-Pekar Spohn conjecture minus something that is small compared to alpha to the power 4. Okay, so one thing I should have mentioned is that in this upper bound I've showed you, this work together with Robert, it is absolutely crucial that we use as an input a statement which has been proven by Stefan Polzer, which tells us that the ground state energy as a function of the square root of p is a concave function. Okay, so if you think about a free particle, the square root of this, if you would plug in the square root of some p in the argument of the energy of a free particle, you would get a linear function. So in some sense, this means that the energy as a function of p needs to, is concave and runs below the quadratic approximation. And this fact that this is a concave function was extremely helpful and was a crucial input in showing that the upper bound actually holds. However, the thing is, concavity, I mean, this is an inequality, so this only helps you in one direction. So as a matter of fact, because we had to use this result from Polzer, we were not able at this point to state the lower bound. So it's really, yeah. So we would have need convexity as well to do the lower one, but okay, of course this doesn't hold. So the other thing is, okay, so I had to come up with a different method, but interestingly enough, so this paper from 24, this most recent paper from myself on the polaron, this doesn't work for the upper bound. So it's kind of interesting that for lower and upper bound, you really have to do a little bit of different things. Now, I think both of them are nice results, which I would love to present. However, in the interest of time, I have to focus on one of them, and I've chosen my most recent work. And the reason for this is that for this proof, there's actually a super simple and nice physical idea. So in the following few slides, I want to show you the essential idea in proving this inequality, and in particular related to a very natural physical picture. Okay. So first of all, we have clearly won once we are able to construct trial states psi. So for every momentum p, we have to construct that trial state psi p, which has norm 1 and such that the energy, the p fiber energy of the state is bounded from above by exactly the prediction of the Landau-Pekar Spohn conjecture, meaning E alpha plus the free energy of a particle which would have the effective mass predicted by the Landau-Pekar Spohn conjecture, plus something that is small compared to p squared divided by alpha to the power 4 in the joint limit of alpha going to infinity and p going to 0. Now, actually, okay. And so so the second inequality you see, this is the interesting one. The first inequality is a triviality because by the variational characterization of the ground state energy, E alpha of p is always bounded from above by this energy. So the interesting inequality is the second one. And once we have this, we can just shuffle the terms around and we immediately get the right lower bound on the effective mass, right? You subtract E alpha and then you divide by p squared and you juggle the terms around and you get the lower bound on the effective mass. So really, all of this just boils down to writing down the correct state. However, what I want to convince you also in the following few minutes is that this is a rather subtle task. And there are two problems with this. So first of all, in the definition of the effective mass, you see an energy increment appearing. So you see a difference of energies. So this means it does not matter whether you want to do a lower bound or upper bound on the effective mass. You always have to do upper and lower bounds on energies because there's a difference appearing. So this is one issue, but actually the second issue, which hurts a lot more, is that you see the right-hand side should be the ground state energy E alpha plus something that is small as p goes to 0. So if p goes to 0, this goes rapidly to 0 as well, which means our ground state or our state psi of p should have an energy that is very close to the ground state energy, which already means that psi of p must be close to the ground state itself. Now the problem is we actually do not have a very good idea how the ground state looks like. I mean, yeah, we do know some some statements where it roughly concentrates, using again Lieb-Yamasaki ideas. But I mean, the ground state itself is not a nice amenable object. So this tells you if you want to have a chance of succeeding, your psi of p must be a modification of the ground state. Okay, so now we need to think of how can we modify the ground state to match this formula. And there is a first attempt I would say everybody should try first. And namely, so in the following, let us just fix the following notation. Psi subscript 0, this should always denote the ground state of the zero fiber Hamiltonian. And then the most naive modification of the ground state is to do no modification. So my modification is to say psi of p is the unmodified psi 0. Okay, I mean, it's a valid definition. I can plug it into I can compute the p fiber energy, and just from some very simple symmetry argument, you see that this is the zero energy of psi, 0 plus p squared. So what you get is E alpha plus p squared. Now you see there is something I like about this, and there is something which is really nasty about this result. What is great about this result is that the p appears as a squared, right? So we have p squared, which is exactly the kind of upper bound we want. So in p, this trial state is great. However, in alpha, this trial state is an absolute catastrophe, because what I'm looking for is p squared divided by alpha to the power 4. Here, I only get p squared, no alpha dependence. So this is way too large, right? Alpha should go to infinity, so 1 over alpha to the power 4 gets rapidly small as alpha increases, and this lacks any alpha dependence. So from the alpha point of view, this is a very bad trial state. You could also formulate it in other words, namely, the only thing this choice of trial state tells you about the effective mass is that the effective mass is bounded from below by 1 over 2. But 1 over 2 is just the mass of the non-interacting electron. So the only thing we have shown at this point is that the effective mass has not decreased. But this is very far from showing that it actually diverges in the fourth power in alpha. So, okay, our first attempt, I think it was a valid attempt, but it's clearly not sufficient. Now, before I tell you how to modify it, let me pin the problem. Namely, there is a clear issue in the definition of the Hamiltonian. You have 3 terms appearing in the Hamiltonian: the kinetic of the electron, the internal energy of the polarization field, and the interaction. And you see, in the first term, in the kinetic energy of the electron, the total momentum variable p is appearing without alpha scaling. And this is exactly the problem, right? You have here a p, and this p exactly translates to the p square you have seen in this very bad trial state. So you see, the only way to get a p that gets small with alpha is if we can get rid of this nasty p that has no alpha dependence, right? And you see also this comes as a square. You have p minus field momentum squared. So since this comes as a square, the only way to get rid of the p without a scaling is if there is a cancellation between the total momentum of the system with the momentum of the field. Okay. So now, at least formally, we know what we have to do. We have to look for a cancellation between total momentum and field momentum. Now, I want to explain this problem to you on 2 levels. I first want to explain this in the physical picture. And here, what we need to do is we need to transfer. We need to transfer the total momentum of the system, and we need to put it only into the polarization field of degrees of freedom. And this is actually very close to the process I would imagine in my head. So this is okay. This is just what I would think, but let me paint you a picture. You have an electron traveling, non-interacting through space, and then it enters the medium. Okay, so the electron, it has a total momentum, and it enters the medium. And due to the interaction with the polarizable medium, the electron will be slowed down. It will transfer momentum into the medium. And this exact process of the electron starting to interact with the medium, slowing down, transferring momentum, is exactly what we is exactly what we would consider as an effectively increased mass, right? So an effectively increased mass means that the electron gets slowed down. So you see in the physical picture, this is actually the fact that we need to transfer the total momentum into the polarization field is actually a very natural thing to do. Now that we have understood it on a physical level, there is of course the question how can we implement this mathematically? And for this, let us simplify the situation for a second. Let us just think about a single particle in R3. So the Hilbert space would be L2 of R3. And how can you boost a particle in R3, right? You have the Hilbert space L2 of R3. How do you create, you have a state, you want to boost the state. Well, this is very familiar. The way you do it is you multiply with a phase, right? So if you have a state, you want to increase its velocity or momentum, you multiply with e to the power ipx, right? And in principle, we do exactly the same. The only difficulty is that we don't have a single particle. We actually have a Fock space. So we have many phonons flying around, and there are now many different choices how we can boost our system. And the big difficulty will be in all the possible ways we can boost the system, we need to pick one that gives the asymptotically right result. Now let me formalize this a little bit. So in order to achieve the desired cancellations, we want to use a unitary boost group. So this means e to the power ip times some self-adjoint operators b, where the self-adjoint operators b are chosen in such a way that they satisfy the boost relation. The boost relation means that if I take the momentum operator of the polarization field and I conjugate it with the boost group, I get the field momentum of the field shifted by the parameter of the boost group P. Now, I would love to write an identity here. The only problem is this approximation, this can never hold as an identity. And the reason is very simple. Namely, the problem is the vacuum. Because of the vacuum, the total momentum operator has an eigenvalue. And since you shift this by plus p, it would mean that you would have an operator that has an eigenvalue at every real number p, and this cannot happen. So this wiggle line really needs to be a wiggle line. So you can only hope for this as an approximation, but since only the vacuum makes a problem, this is not a problem. Okay, so given we have found a boost, we are in principle done, or we are in a good shape, because if I now look at this was the problematic term, right? This was p minus field momentum squared. This is the kinetic energy of the electron, and this was making problems. And now if I conjugate it with the boost, all that is left is the field momentum squared. But the good news is there is no p without the alpha scaling appearing anymore. So we have actually managed to annihilate this bad p term. But of course, you still have to compute the energy of the state in all of the different. There's not only the kinetic energy, there are also the particle number and the interaction energy. And depending on how you choose your boost, you will get different upper bounds. And now the task that is left is to optimize in the boost operator. So you have to choose the right boost to give you the asymptotically sharp result. And this is actually super problematic, because if you choose your boost poorly, you will actually end up not only with a wrong alpha scaling, but you even end up with a wrong p scaling. So, okay, first of all, let me tell you that I am a priori restricting my allowed class of operators by just considering multiplication operators, right? Just in the situation as L2 of R3, where we multiplied with a phase, I say also in this more complicated situation, I want to take B as a multiplication operator. This is not a necessity. I would imagine you could perfectly well choose an operator which is not a multiplication operator. But I do it for two reasons. First of all, it's good to make my class of possible operators smaller, because in the end I have to find a choice. And the second reason is that multiplications operators satisfy exact relations when I conjugate with derivative operators like the total momentum. So advantage one is it's a smaller class, and since I have to pick something, it's good to have a smaller class. And the second reason is it's technically easier. Okay, and of course, you cannot choose any multiplication operator, right? Because you still want to satisfy the boost relations. And it's an easy exercise that this boost relation is satisfied everywhere identically, except on the vacuum, in case the function with which you multiply, this function b, is translation symmetric in the sense that if you shift every input by some fixed number t, the total number is shifted by t as well. Okay. Now, there is one most natural candidate for a for such a multiplication operator, which probably everybody would think first, and that's just take the mean value, right? Let's define b, the function b, just as y1 plus y2 plus y3 plus yn divided by n. Of course, if you define b as the mean value, this relation would be perfectly satisfied. However, and here is the nasty thing, if you would actually take the mean value, you would get not only the wrong alpha scaling, but you would get something that is linear in P and not quadratic. And I don't want to get too much into the details on this problem, but in principle, there is some infrared problems. So the electric dipole field is not decaying fast enough to make the mean value a nice finite quantity. Okay. Now, I want to use my last few minutes to give you a rough idea how you can choose the right boost operator. Now you have seen, if you remember back to the statement of the Landau-Pekar conjecture, you will remember that I've told you that it's alpha to the power 4 times this constant MLP. And MLP emerges from the underlying semi-classical structure. And this is exactly the key input. So what I do is I say, okay, this quantum problem is too complicated. I don't understand how to pick the operator B. So what I do is I first translate the problem into a semi-classical problems. So meaning instead of operators, I talk about functionals. And then I solve the semi-classical problem. So I find the right semi-classical boost, which is much easier. And then in the final step, I say, now that I have the right semi-classical boost, I promote it back to a quantum operation. So I first go to the semi-classical picture, I solve the semi-classical problem, I go back into the quantum world. And I want to show you a small table of correspondence. So in principle, all of okay, so on the left-hand side, you see a bunch of quantum objects, and we have seen them already in this talk. So we have the Hamiltonian H. I spent a lot of time defining it today. We have the ground state energy alpha, we have the ground state psi 0, we have the boost operator B, and we have a unitary group, or like a unitary orbit. Yeah. And now it is well established at this point that the quantum operator H, for example, having a look at the paper from Lieb and Thomas, that this operator H corresponds on the semi-classical level to a functional. So F takes L2 functions phi as an input and assigns them a real number. And what you do is you take the 2 norm of phi, and then you add the infimum of the spectrum of some Schrödinger operator, which depends on this function phi. Now, the ground state, if you believe the first line, then the second line should naturally be that the ground state energy corresponds to the infimum of this functional, which is exactly this constant Pekar that appeared already in this work from Donska and Varadan. Okay, great. So, and actually we know that, so the second line, the statement of the second line is, this is the Donska-Varadan paper, right? The proof of this. Then the third line is, okay, if we believe everything, then the ground state should correspond to the function phi Pekar, which minimizes this functional. Okay, very believable still. Now, generally, you know that operators correspond semi-classical to functionals again. So instead of having a boost operator B, we have a boost functional, which takes L2 functions phi as input and assigns them a three-dimensional vector. And now, you know, we have the boost relation. We cannot take any boost operator B. And the boost relation on the semi-classical side just reads, if you feed the function B with a function phi that is shifted by some value z, then you just get B of I plus Z, right? So it's still translation symmetric in some sense. And finally, the unitary semigroup just corresponds to a Hamiltonian flow, right? So instead of having commutators generating your dynamic, you have this Poisson structure generating your semiclassical flow. And now that everything is semiclassical, I just have to optimize the semiclassical problem. So let me maybe show you still, yeah, let me still say this. So inspired by this table of correspondence, we now look for a boost function B such that f of, so you take the Pekar minimizer, you let it flow by the boost, which gives you a new function at P, and you now want to optimize this function B such that you actually get the right prediction from the Landau-Pekar conjecture. And now, okay, and once you have this, you construct a quantum counterpart to this function B, and you take the unitary flow, and you see everything I've said until this point is basically the introduction of my paper. And this small statement which I have here, you use the correspondence principle to show that the quantum increment is asymptotically equal to the semiclassical increment. So this is like 60 pages, right? So this is, you could say this is the main body of work, but this is, okay, I mean, this is honest work. You have to justify semiclassical approximations, which relies on understanding where the state psi concentrates, which again boils down to a lot of Lieb-Yamasaki arguments. Okay, I think this is a good time to stop so that we also have time for some questions.
Okay. Thank you very much for this beautiful talk about a very nice result, solving an old open problem. So are there any questions or remarks? Cannot see. Everything was so clear that nobody is asking questions. So you told us about the lower bound. Maybe you tell us also a few words about the upper bound, if it's, I mean, possible
Yes, yes.
to do this
Thank you.
without
Yeah, of
black
course.
holes.
So let me go to this picture I've drawn you here. So the thing is, so both also the upper bound relies a lot on the semi-classical correspondence principle. However, the problem we had for the upper bound is that we've proven a semi-classical correspondence principle, so we're able to compute the energies E alpha of P up to errors that are small in alpha, right? That is what semi-classical gives you. So we could say, okay, E alpha of P is like E alpha of 0 plus something that is alpha minus 2 plus something that is alpha minus 2 minus epsilon. So the thing is, we could control the energy very good in alpha, but we had no P control. So this means if P gets very small, then an error of the form alpha, even alpha minus 4, if P is very small, is still way too large. So in some sense, for the upper bound, we really had no control how to handle small p's. So in some sense, if you look at this graphic I have here, you should imagine that there is like around 0, there is a forbidden strip which we could not control. But as soon as the momentum was a little bit larger than the strip, we could really show that the blue and red line align very nicely. But the problem is we had this forbidden region of small momenta. And and we were using semi-classical. So we were in principle doing a Bogolyubov approximation. So we're going to the alpha minus to the next order correction. So we're doing semi-classicals, but then we improved the semi-classics by showing the Bogolyubov corrections. But this still left us with the forbidden region of small p. And the only thing that saved us was this result from Steffen Potzer, where they showed this concavity of the function. This allowed us to extrapolate our results to the forbidden region of small p.
I see. So you cannot escape completely the Feynman-Katz formula and the
Exactly.
probability perspective.
Exactly. But I think this was nice. I mean, it's nice to have two sides contributing.
Yeah, sure. Any other questions or remarks?
Very nice lecture.
Oh, Elliot.
Thank you very much.
Great. So, Elliot, do you have a question or Can I?
No, it's wonderful.
Okay, that's nice
Thank
to
you a lot.
have you here. It's wonderful to have you here. So
Uh,
yes, then can I ask a simple question?
sure.
May not probably not simple. So you said that you choose this boost operator first by going
Oh, yeah,
to this semi-classical thing, and you wrote
exactly.
down all these minimization problem and things. But even this doesn't look easy to me. So is this something doable? I mean, these minimizers explicitly and compute these be
So this is a
explicitly
good
in this
point.
semi-classical limit?
So actually, there is a paper from
Mm,
Robert Seiringer and I
mm,
think Simone Rademacher where they were looking at the semi-classical problem. So they forgot about quantum and they really just looked at the semi-classical problem and they
mm.
wanted to see the effective mass there. And
Okay.
they basically found out that um, if you plug into the semi-classical functional the Pekar minimizer plus something which is of the form gradient of the Pekar minimizer divided by the right constant,
Mm,
you
mm,
actually recover the right energy. So this
mm,
follows from their work. So in some sense, I knew that all I had to do is to find a boost operator B such that the Poisson bracket exactly gives me this gradient of phi Pekar divided by the right constant.
mm,
So in
mm.
some sense, I already knew what I wanted to see from the Poisson's bracket.
Uh-huh. So
And
the choice is unique in this semi-classical case.
no,
Is
no,
that
no,
true?
the choice is
No. Oh, you
no.
still have some choice.
You still have
Mm,
some choice. Yes, maybe I can
mm,
quickly show you the
mm,
final construction. So
mhm,
So here I explained that the mean value, which is like a natural first idea, completely fails because if you multiply the Pekar minimizer with the position operator, you're no longer in L2, but the correction to the energy you would get is the L2 norm exactly. So you get that you have an infinite, yeah, you increase the energy by something infinite, so this would correspond to an effective mass of zero. So
mm,
this is very bad, of course. And the problem with the mean value is this infrared singularity. And so this idea we had was to say, okay, so basically high school statistics saved us. Instead of taking the mean value, we took the median. So what I mean
mm,
with this is instead of integrating this measure over the full space, we only integrate it over a bounded region, but we choose the bounded region dependent on the measure. So it's basically you take the 0.25 quantile, you take the 0.75 quantile, and then you
mm,
only integrate in this region. So this gives you already something that is at least not infinite. So with this, you can see the finite effective mass, and then you need to find the right constant. And
mm,
that's then actually where you have a variational problem because this, the first time you see here, this always gives you the right alpha scaling, but then you can always modify any choice by something translation invariant. And the most canonical translation invariant object you could take is just integrate a measure over a function where you shift minus the median, right? So
mm,
this is always for any function f, this is a valid manipulation, and then we actually optimized in this f, and this is then very explicit. And then in the end, you have this function g. You want to
mm.
make it a quantum operator again. So instead of plugging in this measure rho, which is like the Pekar minimizer measure, you plug in the empirical distributions of your phonons. And that's how you go back.
Okay, thank you very much.
So, any other questions? Then maybe let me ask the following naive question. You mentioned Bohr correspondence near the end of your talk, but the Bohr correspondence would be the Planck constant going to zero, and you have always alpha going to infinity. So is it somehow the same, or
Yes,
can one understand it heuristically?
yeah, so this is the nice thing about the Fröhlich model, which also holds for the massless Nelson model, namely that the strong coupling limit alpha going to infinity corresponds to a semi-classical limit. So you're right. So I always, if we go back a second to my particle number operator, or to my, where are they? Yes, to my annihilation creation operators, I bake in this 1 over alpha. So if you take this, if you want to look at the CCR, you get it within 1 over
Ah,
alpha square. So this is exactly
ah,
your
okay.
Planck.
I
Yeah.
see. Okay.
But this is because I mean, in the Fröhlich polaron, we are in luck because in general, the strong coupling limit is something very different from the semi-classics.
Okay, I see. This makes sense. Okay, any other questions? If not, then let's thank the speaker again.
Thank you.
And I think that we can stop the recording and maybe have time for informal questions.